It's great to be back here again. So I kind of deliberately chose this title, which almost reads like psychotic, but I don't necessarily mean anything else other than that. So basically, what I will try to do is talk a little bit about this model, which goes under this acronym of SYK model. And to be honest, I am really taking not even baby steps into this and still trying to wrap my head around it, what this is about and what it might have in store for us. So what I will talk about or try to talk about today is actually a very simple question, and it seems that there's a very simple answer to that. But of course, the more sort of important and more intriguing questions, they kind of remain open, and I will not really be saying anything about those. Okay, so mainly I will talk about something to do with this chaotic behavior and what global charges or how they affect this chaotic behavior within this within some simplifying approximations of this sort of model. That's essentially the goal. Okay, so collaborators. So this is something I have been trying to do with a few people in HRI. Particularly Ritobroto Shubhronil, they are both students, and Dilip. And we have been, as I told you, trying to wrap our, or maybe more, I mean, I'm trying to wrap my heads more than they have been actually to understand this. So basically what I'll talk about today is mostly based on a paper that we put out and has something to do with a very particular question that we want to address within this model. And of course, there are ongoing things that we are doing. I'm not sure whether I will really be able to say something there, something useful or useless in there, but we'll see. Okay. By the way, I should tell you that you should interrupt me if you have any questions, comments, and considering the expertise that already exists in the room about this model, I hope to learn something more than. Okay. Okay. All right. So that's the basic bottom line. Well, I have not said anything physics yet, but that's mostly structural bottom line. So this is what I will try to do. I will this is a rough outline of the talk. I will start with some motivation and introduction, and there will be some standard words about this, and some of my you might say some of my prejudices that I will try to sprinkle in here. And then I will, but this is going to be slightly long or longer than usual introductions. So yeah, and then basically I will introduce this model, which does not really need an introduction, perhaps to this audience specially, but nevertheless, for my sake of completeness, and what we want to do there with this model, and then I will move on to again some very basic features or very basic ideas of chaos, and particularly in terms of this so-called 4-point out of time ordered correlation function. And then I will talk about how you can extract something particularly quantitative to denote this chaos behavior, namely a Lyapunov exponent. And the treatment here is essentially semi-analytic, and that's really one of the points of what I'm going to talk about here is. So it's not it's a very simple problem that we are trying to solve, or simple statement that we are trying to make. And then I will try to end with conclusions, outlook, etc., etc. So that's the rough outline. Okay. So this is the standard motivation, which is, I think, very interesting motivation. The motivation is essentially a very simple question: which of the quantum field theories have holographic dual, and if it does, what is the dual description? And we know the examples. For example, in no particular order I have arranged them in this vertical direction, But for example, the very well known examples are ON vector models, so to speak, which we know have a dual description in terms of higher spin gravity. This one we also know pretty well by now. This is the if you like standard, or this is the original ADS CFT correspondence. It has to do with SUN gauge theories, which is essentially dual to Einstein gravity, just standard gravity theory with some matter, etc. So that's a very standard picture. The features here are between this and this. There's a difference. Well, other than the vector or the gauge theory part, is that these ones, they have large anomalous dimensions, and that essentially gives us a classical gravity. On the other hand, the first one here, they have very small anomalous dimensions. So therefore, you get gravity plus all spin degrees of freedom also. Nothing decouples. This is all in the, yes, I should have said that, yeah. Everything I mean is, you should always, I mean, nothing is going to be small n or order 1n, order, yes.
Very sorry because I'm
yes,
jumping ahead, but
yes.
Just to check with you, I mean, a striking fact about SYK and also about SUN, which we know from the gravity science
Yes.
for n equals 4 is you're close to meeting the chaos bound, or you meet the chaos bound.
Yes.
But in the ON, you're nowhere close, right? And I mean, that's much more easy, right?
That's true. Yeah. Yes. So I will not actually.
Towards your comment about something interesting, perhaps.
Right. So I will have nothing to say about the vector theory at all, neither this one. And about this, I have absolutely nothing to offer on the right hand side as well. But this is just a standard motivation. And here one of the in between parts is the one that you said, and the other thing is that anomalous dimension is order 1 here. It's neither small nor large. Okay. Now, there are interesting features of this model, or interesting / encouraging features. 2 of which, this is a standard list of 3 features that usually people enlist. However, 2 of these, at least I have spoken with a couple of condensed matter colleagues. They say that these 2 features are not really very unique to SYK. But nevertheless, so the point is that this model is solvable in a certain sense, that the Feynman diagrams you can sum up into an exact Schwinger-Dyson equation. And if you can solve that equation, you have solved the problem. That's the essence in which this is solvable. It also has emergent conformal symmetry in the IR. Actually, it's not exactly conformal. It's nearly conformal, but okay, we will not make this distinction any more precise.
There's another model that has the second feature?
I don't know of the name particularly, but at least, yeah, I think so. That seemed to be the claim.
Just to understand, of course, there are many examples when you get conformal symmetry in the infrared, but
Yes.
I thought what's important here is that you can't decouple the ultraviolet, right, fully in the SYK, because the cutoff comes in. You
Oh, I
can't
see.
really neglect the kinetic energy term. And that's what I thought was sort of an interesting twist on normal CFTs here.
I see.
And again, I mean, it's not that easy to get conformal symmetry in quantum mechanics.
In quantum mechanics. I see.
Because, in quantum mechanics, if you've got conformal symmetry, either you've got only ground state, or you've got the whole continuum. But only ground state kind of thing is okay in quantum mechanics, which is okay. But this kind of thing often means that it's not what your people say. I don't know of another. I mean, I'd be very interested.
No, I don't know either.
1 over x squared potential, yeah.
This Furlan,
Yeah.
this original,
Continuum all the way to minus infinity.
yeah, I think in that sense, condensed matter people say that you can actually write down something else which is not the SYK, but still has conformal symmetry, which is the conformal quantum mechanics.
Quantum mechanics.
Yes, for example. So that way, this, I mean,
So maybe Shirazi's trying to write there, the quantum mechanics will perhaps never decouple unless it's some pathological system within.
I have the feeling, because it should be that every quantum mechanics is dual to ADS too.
No, well, at least, yeah.
A conformal quantum mechanics.
But may not be weakly coupled.
May not be, but ADS too has this general feature. If you add the matter to it,
Yeah, that's what
Yeah.
I was
Yeah.
also,
yeah.
In the case where you have constraints, you can decouple.
Yeah. So there you can
But that is like a really strange or very boring object, right? In a theory, you just have a ground state, nothing else. And it's
Don't
sort
say
of.
that in HRI, you know.
Okay.
Sorry.
Well, yes.
But you know, the interesting thing is that that the same system that Ashok described with the theory with only ground states is also a system that Juan is describing with this thing.
No, but the Schwarzschild action is also because Ashok didn't have it.
He didn't have that, but it's in the same system. It's a near to be unless you know this one. But I mean just nearly supersymmetric black hole.
Yeah. But I'm just saying Ashok just kept the ground
He
state.
kept the ground state, but the same system was a little bit off of extremality.
Yeah.
So somehow there was some sort of truncation to that, which I never completed.
Yeah. It's I think order of limits.
Yeah, somehow, yeah.
But can you kill off the highest finite energy states by taking just an order of limit? You can.
Go to the exact ground states.
Oh, but then you will be just left with the ground states and nothing
That's
else.
what Ashok came.
Okay.
Yeah, but you know, the actual physical system doesn't have a mind. But anyway, maybe later. But it's left. It's described by this stuff, right, which has states all the way down. And yet Ashok zero in on that ground state, and that's completely other.
Okay.
I mean, but
So-
still some of them you can really take the I mean, gravity tells you you can. His entropy function is that.
It's all correct.
Okay. Yeah. Yes. Okay. So just to say that, I mean, this part was in the sense that this what is called this DFF, this original conformal quantum mechanics, is also one of these. But nevertheless, this part I don't think anybody has calculated, or at least not to my knowledge, this chaos exponent for conformal quantum mechanics and so on, the traditional conformal quantum mechanics. So I don't know what happens there. So that I don't know. But nevertheless, I mean, in this model, people have managed to calculate this and this exponent, and which I denote by this lambda sub L, and it's equal to a certain value, which is nowadays said to be saturating the chaos bound, because the conjecture is that your lambda L is at most this. It cannot be more than that. Yes, that's right. Yes.
So in that sense, isn't the distribution system that full symmetry is broken spontaneously to
That is true. That is true. Yeah, that is true.
so would you expect similar system in general?
I don't know. I don't think so. Generally, I don't think that would happen.
But once there's one part of the full parameterization system,
I don't think it is.
Yeah. That is true. That is true.
Just to ask you, of course, this is a very important thing, but something prior to this even, which is that the system SYK model thermalizes and
Yes.
gets calculated,
Yes,
is already very non-trivial.
that's
right?
true.
I mean, are there more condensed matter systems, say quantum mechanics or otherwise known, which are shown to thermalize and yet are calculated?
I don't know.
Conformity. CAR-Ts, which I think automated. In the CAR-T calculus, you start with the bounding state, then you conformally and various conformity.
We're talking about 2D CFTs.
You show that it's
Yeah, fine, calculated density exchange. The full overlap between, you take a certain region, you compute the density matrix, the overlap between that and the density matrix, and so forth. It's very fast. But, yeah. Some of this one.
But that has not, similar thing has not been done in one dimension, right? And I don't know whether it will just carry through or some subtlety will.
One dimension is interesting because it's solvable, not just because.
Yeah.
I mean, it's not particularly interesting for being.
That's That's right.
If you look at the boundary of a two-dimensional space, that would have a closed invariance, right? And some of components would make it simple. And then you would have to look for more dimensions.
Yeah.
Yeah.
Or would it just be universal in this part?
I think you would have to break the time.
No, but would one be able to construct the various models of this type, or would one just be the universal answer?
Oh, I see. Let me sort of maybe I was thinking, my understanding is that if you do have the breaking of time reparameterization invariant, then that term dominates the variability.
Yeah.
Right? I think that's the general feature, unless the coefficient is something strange.
Somehow
It's
suppressed.
enormously whatever, big or small. No? In terms of scaling, then not that.
And only that contributes to this chaos.
Yeah, dominant contribution.
Yeah.
But then, sorry, just
Yeah.
to ask about that, this thermalization doesn't, I haven't internalized this, the thermalization feature of SYK doesn't use the Schwarzian action per se, right? I mean,
No.
that is,
For instance, the quasi-normal mode time scales again are 1 by temperature. It's not some universal number.
yeah. So in a sense, now that we understand the breaking of time reparameters and invariant, the chaos bound, while spectacular, sort of follows some symmetry consideration. But the normalization is sort of really detailed feature.
Yes. I think so.
Still somewhere.
I think so. Yeah.
Then you study black hole formation. What exactly is it?
Yeah. Okay. Yes. So anyhow, I think this is at the well, I mean, I prefer this better than I know what I'm going to talk about, so there is nothing for me to learn from there. So, okay, good. So yeah, my personal feeling is that all three together certainly puts this particular model and variants of this on a very interesting and if not unique status. But okay, so that's the feature part. Now, of course, this model which I have not introduced yet, but still on the motivation part, in some sense, this is essentially a 0 plus 1 dimensional object. Therefore, it's just a quantum mechanics, and we know that if it has to have a gravity dual, there has to be some role of two-dimensional ADS in there. And there are two canonical ways in which we can see ADS2 emerging in what I might call standard holography is well, or if not standard holography, but there are two ways we see often that ADS2 emerges. One is, of course, if you take extremal limits of black holes. That's one where you get an ADS2 factor very naturally. The other one, which I will use more for my motivation in some sense, is that if you want to talk about in the standard ADS-CFT kind of context, some infrared description of a finite density system which is strongly coupled, there you do see an ADS2 emerge. So that's two standard ways you can see, and I'm also going to take a viewpoint in standard quantum field theory, which often we don't make statements or we don't state problems in this language, but you can if you want. It's an RG picture in the sense that suppose I start with an UV theory, I can always ask what happens to certain phenomena in the IR. Supposing, of course, I know what's happening along the way. So if I have this full picture, I can always ask questions in this framework, which we usually don't quite do. We usually ask questions about Feynman diagrams and all those things. So essentially, it's something like in the UV, I start with a d-dimensional quantum field theory, and in the IR, I get an emergent geometry. That's the essence of this. And if you have a density-driven system, which is in holography, it's quite common or quite popular for various reasons, you can get an ADS2 factor here, dressed with other objects, etc. of course, this intuitive picture that I'm trying to paint here is mostly based for me on Einstein gravity-based holographic scenario. I don't quite know what happens in the higher spin theory. That not quite sure. Okay. All right. So I will just make a couple of comments here. This is a highly, maybe completely irrelevant and highly speculative part, but nevertheless, we make it. One particular state, well, one particular case in which you might be very interested in finite density systems. I mean, you can be interested in many other cases, but this is very intriguing for many reasons, as well as physical, as well as experimental reasons, one might even say, is when you have a QCD type system or QCD type Lagrangian with essentially some SUNC gauge theory with flavors, so adjoints and fundamentals both. And why is this important or interesting? That I don't think requires more justification. So there is one particular corner of this theory in which if I don't have any flavors, if I don't have any quark matter, etc., then large n phase of this system is supposedly what is called chiral density wave, and this is a phase which has some spatial modulation, etc. So it's a condensate which spatially modulates that sort of. Sorry?
Condensate of what?
It's a condensate of some psi bar psi kind of thing.
Sorry, I thought you had no clue. Oh, very small number?
Very small number. Yeah, sorry. This no should have been under quotation. Yeah. Okay. And then, of course, that we know is not quite QCD, because in QCD we have NF as large as NC. Same order, there is no separation. And in there, the statement is if I want to do some large n calculation of QCD with matter, in which I do have a new parameter to tune, this is a tunable parameter, which it was very small here, then one can actually show in a certain sense that instead of this chiral density wave phase, one gets a superconducting instability, which is this color flavor locked phase, which is supposedly this color flavored locked phase, etc. So that again is a qualitative picture which one expects to get, and to slightly elaborate on that, I will just make this point, or I'll just have this slide. So suppose you want to capture that within standard holography, meaning the Einstein gravity plus matter. What I could do is, forgetting about all brane, supergravity, etc., I can strip things down to a very simple minded description, in which I have essentially Einstein-Hilbert action in 5 dimensions, and I have a piece here which is this Dirac-Born-Infeld type. So essentially you can think of it like having or being generated by some brane that you may have in the 10-dimensional full picture, and of course you can have some Chern-Simons term as well. And roughly speaking, in this action, in this Lagrangian, this coefficient I can identify with NC square. This coefficient, which is the tension of the brane or originating from the tension of the brane, I can identify as NC times NF. Therefore, this kappa square tau is essentially this new parameter that you can tune. And presumably, if I tune this, and if it really is describing a physics along this line, then I should be able to see some manifestation of that. That's roughly speaking the very qualitative picture. And of course, in this within this action, there's a very standard way to generate or to excite density or chemical potential. That's by exciting a particular component of the gauge field that's living on the brane, on the supposedly brane. So if you do that, then there's a very simple RG flow. So this is essentially the picture that I was trying to say or trying to have in terms of a cartoon before. So I have an UV, which is some d+1 dimensional theory, and if I perturb it by density in the IR, I get an emergent CFT of 1 dimension, where certain directions have completely decoupled from my dynamics, and I don't really need to care about those. All you have here is this, and for the particular case of with this action, there's actually the solution that one finds have some remarkably, well, I would not say remarkably, some very simple yet very intriguing features. One of which is in the IR you get an ADS2 with a flux which is actually non-perturbative in this NF over NC. So if I take this NF over NC to be very small, I would never see this as a solution even. So in the solution space, this is rather intriguing. And there is an interesting instability of the system, which is now if I take this as a really sort of a phenomenological model, I can treat this actually I can treat all the parameters independently as free parameters. And in that free parameter plane, this alpha and NF over NC plane, you can actually see that if you tune these parameters, there's a particular spatial modulation and a particular superconducting instability that you can bridge in between by tuning these two parameters. So you might say that this sort of looks like somewhat that instability in QCD, which you might expect otherwise.
I understand the spatial modulation because you can get these density waves.
Yes.
Because of the Chern science.
Yes.
So, but you don't have a scalar field, so how do you see a superconducting?
Oh, you need to have a scalar field outside of this, yes. Outside of this, yes. Yeah.
And so non-immediate dynamics on the brains is not important for
I think it is important. It's just that I don't know how to effectively capture that yet. So yes, I think it is important, but that I don't know what will happen. Okay. If you like, this is a truncation of the diagonal truncation. All right. So good. So now you can always speculate. The speculation is that could this, not remarkably, could this oversimplified gravity model be relevant for things like QCD? And if you are asking this question, you might as well ask, since I get an ADS2, could SYK actually be relevant likewise, in the sense that there is some QCD feature in which I can actually recover or I can actually capture by doing some local SYK-type analysis. That's the essence of it. However, in this construction, there was a charge to begin with in the story. So it makes somewhat natural, or it becomes somewhat natural to consider an SYK-type model with a charge. That's basically that's one way to sort of prejudicially motivate your model. Okay, so finally the model. This is a very well studied, well represented model by now. So the model is essentially, it has a Hamiltonian, so I'm going to talk about here with fermions which are Majorana fermions. So therefore they obey an anti-commutation relation of this sort. And this Hamiltonian is a 4-Fermi interaction of them, and these J's, these are couplings. So far everything is fine, but there's a very strange feature, or very what should I say? I don't know. There's a somewhat disturbing feature, especially if you want to recast or understand this Hamiltonian as a holographic model, in the sense that these couplings are actually not fixed. They are drawn from certain Gaussian or random distribution, such that the expectation value is 0. So basically, whatever you compute with this Hamiltonian, at the end of the day, you have to do a disorder averaging. So there's an averaging associated. With a particular standard deviation, which I denote by this. So their numbers don't matter. There's a factor of n cube, that's just a normalization chosen, and there is a curly j, which is related to essentially, well, yeah, that's the relation. And I realize that as I go along, this curly j I will be replacing by the usual font capital J. So you should not be confused. They are the same thing. And of course, this is the original SYK-type interaction, but nothing really stops you from taking this model and generalizing it to a Hamiltonian like this, in which you actually have q number of fermions interacting, all of them Majorana still, and with a coupling of this sort, they are still drawn from a Gaussian distribution like this, and therefore you get a Hamiltonian of this sort. This factor of I is just there to make things Hermitian, and that's a very standard generalization that one does. So what it does for you is introduces an additional parameter, which is q, just a number to play with. And you can work in the limit where q is very large and n is of course very large. That's from the get-go, that's always the case, such that q is less, actually it's less or equal will also work. And what does this give you? It gives you a somewhat, actually it gives you convenience, a somewhat analytic control of the system.
Sorry, I
Yeah.
should know this, but Q is the number of flavors.
Q is the number of fermions, yeah, in the interaction.
And N is the total.
N is the total number, yeah, yeah, yeah. So I could have Q at most N. Now, okay, good. So that's the base of that. That's the basic structure. Now what you can do, if you want to have charges, there are many ways to do it, but one way you can do is just consider complex fermions instead of Majorana fermions. So here, these were all real. Now I can consider, or rather this Hamiltonian. I can just take this and try to generalize it for complex fermions. And you can write down an interaction Hamiltonian like this, where, as you can see now here, psi daggers and psi, they are different objects. So therefore, I have a Hamiltonian of this sort. And the reason for doing this is because if I consider complex fermions, then it becomes very easy to introduce a term like this, which is actually like a mass term, or alternatively you can reinterpret it as a chemical potential. And again, these couplings will be drawn from a random distribution such that this J square is essentially proportional to this curly J square, etc. So that's the basic model. So the theory, roughly speaking, in terms of the Lagrangian, is just this. But actually, yeah, I think that's fine. And given that, so if you like, this is your UV theory in whatever your UV is, the appropriate UV. And if you read off the dimensions, that's pretty easy to read off. The dimension of psi and psi dagger are both 0, mass dimension or length dimension. And this mu and so this coupling J, this curly J or this small j, they are dimension full objects. They have mass dimension 1. So essentially they are energy dimension. And in the Lagrangian, to begin with, if I am to discuss some finite temperature physics, I do have two free parameters. So beta is 1 over the temperature. So beta mu and beta j, they are of course independent, two free parameters that I have at the UV to tune. So this is the model. Very condensed matter like approach. Okay. So if you do that, then you can go along and start defining your things. So for example, the Green's function, the standard Green's function is defined in this way. This is a time ordered of two fields, and you take an expectation value, and this Green's function for the free theory is very easily obtained to be this. This is in the Fourier space. So omegas are energy levels, if you like. This mu is the original mu that we have in the Lagrangian, and in the real space, real Euclidean space, this is how the Green's function looks like. With temperature, so this is without temperature, this is just an expression in the Euclidean time, but if you introduce a temperature, then you can do the Matsubara sum again with standard techniques, and what you end up with is, for the free theory, a certain Green's function which looks familiar. It's like Fermi-Dirac kind of thing. Okay. So what is the one simple way to sort of recast that this theory is exactly solvable is basically, once you turn on the interaction but still remain at large n, basically what happens is this interacting propagator you can recast as a sum of these type of diagrams, which are usually called Mellon diagrams, and this sum, as you can already see, it looks like a series that you can actually solve in this case, or sum up rather. So if you do that, then you at the end of the day end up with a Schwinger-Dyson equation. So basically this is now the Green's function for the interacting theory. So it's no longer free, and inverse of that is given by this I omega plus mu. So I omega plus mu was the free case, and now we have a term which is usually called the self energy interaction, or self energy diagram blob. And in this case, with the complex fermions, etc., this is going to be a function of the chemical potential and the frequency and is given by this expression. So, this expression is not very difficult to see how this comes about. So, this object is diagrammatically essentially this object. So, what is this? This is, so since we have complex fermions, each propagators I can draw with an arrow. And suppose I am considering a process in which one arrow goes from left to right, and I have a q point interaction vertex. So, therefore, from left to right I have one line, and each of these lines, so all the lines on top, the number of those will be q by 2 minus 1, and the ones that are coming this way will be q by 2 minus 1. So, there is one, of course, extra line that is going from left to right. So, therefore, the propagator will have usually g mu comma minus tau. So, these are these lines raised to q by 2 minus 1. So, that is those lines, but this one will have all of them and then one more. So, hence that is the diagram, and there are two interaction points here and here, therefore, you get a factor of j square. This minus 1 raised to q by 2 is nothing but the term that is coming from this taking two vertices. So, you get an I square which is minus 1 raised to q by 2. Yes. This? Yes. 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 You want to have a matrix, or you want to say you want to have a matrix, mass matrix kind of thing, and you want to say that the mass matrices I am going to take as random. I think you can. But that's.
But if you want to regard it as trace e to the power minus beta h plus mu q, you could do that. But suppose you want to regard it as trace of e to the power minus beta h plus mu q, then that q has to be a conserved type. And for any given j, there's only one conserved type.
Yeah.
Meaning replacing the all sides and all sides, because the j is coupled down. Okay, so it's not like there's many charges that you can turn on independent chemical potential. Of course, you can further break the symmetry of the model, but you should then should think of it as a chemical potential.
Yeah.
You could constrain j, suppose.
You could constrain more, and then you could have.
Yeah.
Yeah, basically you can have a larger symmetry and then larger.
That's right. Okay. Yes. So, yeah. So, this is what, okay, good.
The left hand side should be sigma of tau.
Yes, sorry. Good, yes. So, yes, for reasons of, I guess, convenience, one of these equations is written in the omega space, the other one is in tau space. Okay, so and this should have been tau. Thank you. Okay, so the point is, of course, at the end of the day, you get these two equations, which are Schwinger-Dyson equations, and essentially these are the two equations that you have to solve. And you can, given these two equations, you can solve them for any value of q or for any value of mu, etc. But that solution usually tends to be a numerical one, and that is not to say that you cannot solve that or you cannot gain physical intuition. It's just, if you are not into numerics, it's just inconvenient. In there, what happens useful is if you take this parameter to be really a free parameter and try to take a large q limit, then this problem becomes much more tractable in a certain sense. So, what I am saying is that given these two equations, again this should be tau, one can actually solve this for any value of mu, any value of q, any value of j and whatnot. But those solutions usually turn out to be numerical. So, your approach, in order to solve these equations, you have to do numerics. But here, so taking this interaction, number of interactions, for example, to be a parameter, what that allows you to do is actually make a series of these variables, if you like, and then solve it perturbatively in 1 over q.
Even at an arbitrary q at low energies, you can solve it.
At low energies, you can solve it exactly.
I
That is
suppose
true.
it's the same here, Pooja.
At low energies, you can solve it exactly. That is true. But for if I am staying at arbitrary energy, then taking large Q, I can also solve it exactly. Semi-exactly.
But I'm asking now, when you turn on the chemical potential, is
Yes.
there some low energy sector which you can still test
Yeah,
and solve it?
yeah, yeah, yeah.
And is it the same as what you do without a chemical potential, that is you self-consistently assume that sigma dominates over
That's right.
both omega and mu?
Yes.
Is that right?
Yeah.
And that turns out to be
That turns out to be the conformal limit, if you like. Yeah, exactly.
Now that the technique are two limits, would you not have done a cooling limit for keeping in over taking both to be long?
Keeping n over, that is what I'm essentially doing, right? I have already taken in large.
Yeah, but where is n over q?
So, oh, you're asking where is n over q? That is not clear in this equation. That you're right. Now, what you can say is, suppose you can assume that there is a well-defined 1 over q expansion, and say you solve that, and then you can make sure that whether that solution is consistent or not. So that's the way you solve it.
This is asking, perhaps you've taken n going to infinity first, and now you're taking q
That is right.
to large.
That is right.
So there might be another limit where you take n and q both to infinity together, keeping one over q fixed. So is there another limit of that?
Yeah. But I guess that would be not practical because you lose linearity.
Yeah. Well, I'm not sure you lose planarity, because I think planarity is ensured by large n.
Yeah, so, okay.
You could take that. Yeah, yeah, your question is valid. I don't know if I, from the get-go, in terms of diagrammatics, I start taking that limit, what will happen? Yeah, that.
Because then there will be a parameter.
Then there will be a parameter, precisely. Here it's done like a double expansion. You are saying from the get-go, I take one single expansion. Yeah, yeah, yeah. I don't know the answer. Good. Okay. So now let me actually very briefly say what we mean by chaos. This is something that, well, I have honestly never understood, but what I know is classically we talk about chaos of trajectories, and by trajectories we mean that we start with some initial condition and see that if we vary the initial condition slightly, what happens to the final evolution. And the statement there is that if the final evolution is exponentially sensitive in terms of the initial data, then that system is said to be classically chaotic. So basically, this is the classic example of this is taking the billiard board and studying trajectories of balls inside, etc. So if you want to take this classical statement and promote it to something quantum mechanical, what you can do is you can immediately interpret this derivative as a Poisson bracket, and once you know the Poisson bracket, then essentially you go from there to the commutator. So so then in terms of quantum mechanics, what happens is this commutator must behave like this, that is your diagnostic, if you will, of a system, of whether a system is chaotic or not. And to make, because of these factors of I, etc., you can actually square it up to have -1 in front, and then define this C of t, which is expectation value of a commutator squared, which is then what you use as your diagnostic of chaos. So this is basically something that will go as e raised to 2 lambda times t, and you read off the lambda for the systems that you can. So you can already see that this is, in order to evaluate this commutator, you are actually calculating a correlation function which is not time ordered. So therefore, essentially at the end of the day, it boils down to a calculation where you have to do a out of time ordered correlation function. That's the whole point. And this calculation was surprisingly enough was done initially in 1969, I believe, in a paper by Larkin and Ovshinnikov. They had other motivations. We're talking about superconductors and whatnot. Yeah. So no. So this square is just done to get rid of this I. So if I just square this up, I don't think it's fundamentally very crucial.
But I mean, you're going to take an expectation value, let's say that's for the last time.
Yeah.
So you may have something that's non-zero, but phases will over let's say it will conspire into something. You want to get rid of trivial zeros because of that.
Yeah. So you sum over positive definite numbers.
So you want to keep that from modulus.
Module, yes, that's the right word, precisely. Good. Okay. So, all right. So now, okay. So what we have to do is, yeah, yeah.
Curiosity, because as you are saying, one doesn't grow up computing all kinds of correlation. So one
Yeah.
intuition, if you were doing a neatly coupled theory like lambda phi 4 or something,
Mm-hmm.
this is not a system one believes anywhere close to chaos.
Right.
What do you get? You don't get an exponential at all. In perturbation theory, I guess you get a power law, but
Yeah.
you believe to sum to an exponential, maybe not anywhere near the chaos bound, but or is it not even supposed to be exponential because the system is nowhere near chaos? Does one know how this is usually?
I think it's not always exponential, at least. Not always exponential. Actually, this is something I completely don't quite understand as well, because this statement that, this, suppose somehow I calculate this, and I don't find that there is an exponential behavior. That does not always mean that the system is not chaotic. So the statement really is that I have to calculate all possible such objects, and some of them may behave this way, some others may behave some other ways. So it's a very
In a dilute gas, like in air, even in a weakly coupled limit, you would expect that some. This molecule will be hit against basically actively.
I thought this is like you have one trajectory, and then you will slightly displaced trajectory, and you follow it for a long time, and you ask
Right.
how far apart are the two.
Right. So suppose I take some gas, position of gas molecules, I take slightly different position of gas molecules. Because the collisions are sort of timed collisions. Every once in a while, even the slightly displaced one will deviate quite a lot. And that will, I think eventually, you wait long enough, so something like billiard balls and so on, that kind of system. I think eventually, even if weak coupling, even in kinetic theory, I think you'll eventually find it. Maybe very small. And this would be mine. I'm not sure about pi to the 4, but to the extent that it behaves, pi to the 4 is supposed to be governed by Boltzmann transport equation. So your question is, within Boltzmann transport equation, do you think you affect that? I would be okay.
At least if you're working with the classical cariants in coherent states, you may not expect chaos. I mean, you have some solution for phi as initial condition. I mean, maybe, I don't know. Maybe the phi 4 is doing interesting things. You're solving it, right? I don't know. Or do you think, so is it that the quantum system is going to show it, but the classical doesn't, or classical phi 4 also shows it? Because
Hard-board billiard shows system of billiard balls with hardcore interaction, even if it's very dilute shows. There's something to it. So to the extent that the Boltzmann transport equation behaves like these billiard balls once in a while collide, sounds like it should. I don't know.
Yep. Yeah, I don't think these things have been made precise or explicit at all in the in the.
You have to go very high on the perturbation theory and resum it so that the law of operator mixing is possible. I think this is then will be exponential.
I see. And then, Spencer, it's believed that, say, even phi 4 in perturbation theory after resumming will show this exponent?
Yes, I think so. I mean, I've not seen it done, but I would imagine that, ordinary perturbation theory is around integral system usually. If you orders, you will not get this type of behavior. Essentially, it's also non-perturbative. I mean, lambda L at least finite temperature goes as 1 upon h bar.
Yeah.
Right. So perturbation theory, you'll have to really do something very drastic to get this type of behavior.
But nonetheless, at any finite coupling, no matter how small, you should see this. For instance, in n equals 4 Young's theory, we know that at strong coupling, we see this exponential behavior. Now let's vary the coupling. Your question is there a phase transition?
Yes.
Is there some finite lambda at which you stop seeing exponential?
What I'm saying is that even if you want to see the deep coupling here, then lambda is not very large, going to infinity, then you have to work very hard in perturbation theory to see a 1
And any given order in the coupling is a power
Yeah.
law. But,
Yes.
but if you summed it up, no matter how small lambda was,
Yes.
you would see an exponent.
I agree. If you sum it up, yes, I agree with you. That's what
Yeah.
I said. Yeah. Yeah. It's a difficult problem.
Yes. Good. So yeah, that way this is nice that it kind of it's easy to calculate in the black hole. Yes, exactly, as always. Well, at least in as many cases.
By the way, just as an aside, the
Yeah,
black
yeah.
hole example also shows us that you can have something which is not quite chaos but sort of there, which is if you do the scattering experiment, calculation for the extremal Reisman constant,
Yeah.
which is not finite temperature, then you replace the exponential by a power law. And
Ah.
so trajectories do diverge, but with a power law, which is a kind of not quite canonical chaos, but
Diverging
zero
nevertheless.
temperature. Yeah, zero temperature. So there might be a new universality class of sort of near chaotic that the black hole serves.
I see.
Anyway, that's an aside.
Okay. Okay. So in there, if I turn on a small temperature, I would start seeing this exponential.
And small you would, but if you rigorously at
I
zero,
see.
you still have a kind of, you have an infinite blue shift or something.
Yeah,
which
yeah.
does result in a big effect, but it's power.
I see. I see.
For higher point functions, would see.
Can I ask a question? Sandeep, can you explain what you said? Because the zero temperature calculations are not done. We don't do zero temperature. We simply sample energy levels, using the finite temperature, as a crutch. So how do you do this type of thing for extremal black holes at zero temperature? I mean, people have done it.
It's a very simple calculation, Spenta. What I was describing is simply that, the scattering calculation that gives you the out-of-time correlation function,
Yes.
which you can do in a black hole background. You can
Yes.
also do it in the extremal case. And
Yes.
the basic reason for the exponent is that you have a non-trivial surface gravity
Yes. Yes, yes.
for a black hole. Now you might think
Yes.
that in the extremal case, because the temperature goes to zero, that surface gravity is going to zero. But actually what happens is that the real physical effect of that surface gravity is that there's a very large relative shift or blue shift, say between the ingoing particle and the one coming out of the black hole.
Yes.
And that still continues to be the case in the extremal geometry. It's not doesn't go like exponential in temperature, but it goes as a power law in the time taken. And what makes up the dimensions are parameters of the black hole. So just that, I'm just saying you can repeat the gravity calculation in the extremal geometry, and you see the analog of large deviation, but power law. That's all I meant. Yeah, I can. Yeah.
Thanks. Thanks.
Yes, thank you. Go ahead.
Sorry, that sort of
Okay.
features with the accessibility with the time mode.
Yes. Yes, and yeah, I think there has been other. Yeah. Okay. Okay. So I forgot. Okay. Good. So at the end of the day, so basically it boils down to be able to calculate an out of time ordered 4-point function, and essentially you have to solve these equations. And of course, the usual or the conformal limit is a limit still in which you take the self energy to be larger than both of these scales. But now the fact that there's another scale in between can actually give you some non-triviality in the 4-point out of time ordered correlation function if you are able to calculate it. So that's the bottom line, and that's what you're trying to do. So what do we do here? Of course, you can go to the conformal limit and do this calculation, but that would be like throwing this mu away anyways. So why did I introduce it to begin with? But if I want to keep that somewhere in the calculation, I can still do a Q expansion. So this is what I was saying. So you start with the Green's function and you assume that it admits an expansion of this sort. And then you try to go back and solve the equations, and from the solution you try to see that whether everything is consistent, and it turns out to be consistent. So that's the end of it. But basically what happens is in the middle is you are able to actually find a solution. So suppose I plug this in, the series in the Schwinger-Dyson equations. What I get is you can recast everything in terms of a simple differential equation. So this is g is the unknown function now that I have to determine at order 1 over q, and it satisfies an equation of this sort, which is very easily solvable. One thing to note here is that this equation is actually very, very simple, except there is only one change, and the change is in the fact that now there appears to be a new effective coupling. So J is the coupling that we started with in the interaction Hamiltonian, and this has been replaced in this equation by something called J tilde. So now the point is that even if I am at large coupling from the Hamiltonian perspective, I may not be at large J tilde, because I can tune this so that this becomes order 1 or even very, very small. So everything is really here. I mean, it's really very, very simple. Okay, so that's the equation, and the solution of that even I can do, and the solution turns out to be this, and this is exactly identical to the solution that Maldasen and Stanford had already discussed within a year or so, I forget.
Yes.
Yes.
J tilde has some scaling with Q.
J tilde has this scaling with Q, yes. Right, and so this is the solution, and there is somewhat of a relation. So J tilde is, so in other words, actually this is not determining J tilde, this is determining nu, this parameter. So this is a solution written in terms of a parameter nu. So one thing that what I already said is that this whole dynamic somehow at large Q in a sense reorganizes in terms of an emergent coupling, which is this beta J tilde. So there's if I start with a Hamiltonian in which I have a beta mu and a beta J, so these are the two free parameters, if you like, at the UV. Down there somewhere I do generate through this through somewhat of a non-invertible map is this effective coupling beta J tilde, and everything at the end of the day depends on that. So you can ask questions in two ways. You can ask questions of what happens with to the Lyapunov exponent, for example, with respect to this parameter, or what happens to the Lyapunov exponent as I vary these two parameters independently. I can ask this too. Yeah.
In usual SYK-J determines in a sense when the deep infrared theory couples to the more ultraviolet, right?
Right.
When the truncation to the deep infrared.
Right. Right.
And so you're saying because of this map, it can be that J might be small or something,
Yeah.
but J tilde could be big.
Uh,
Does it go that way?
no,
or
it cannot go that way. It could be the other
so
way.
that even
Yes.
if J were big, mu makes it.
Mu makes it smaller because of this. Because this object cannot go small. So this thing that is in the denominator, this cosh of beta mu, I cannot make this small so that J is say order 1, but this becomes large. That will not happen, but it will go the other way. I can take J to be very large, yet I tune this to make this very small.
And you might come to this probably, but is it tied to the fact with fermions at chemical potential you expect some kind of a Fermi surface? Of course, you're in 0 plus 1D, but therefore it gets easier to have gapless excitation in a sense, so the deep infrared gets more secluded from it. Anyway, I may not really say anything very more specific than what you already said. Yes, yes, that's probably what it is. Yeah. Good. Yes. The way this is carried out, the way this expansion is carried out, you can actually go to a higher order, and it will become very clear immediately that this coupling is really fixed by the leading order 1 over q correction. So it will not change. Okay.
So wait, so was the final conclusion that the answer was the power law in the d pi r again? Did the powers change?
Sorry, power law for what?
For the 2-pi function.
Oh, for the 2-point function, it's still this.
And
Yeah, I think so.
Can you take us to the IR and show us?
For the 2-point function, you're going to have to derive it. So, okay, so the IR would be, okay, let's see. So, in some sense, yes, I think so. I think so. So,
Hasn't changed from my sense.
uh,
Apart from a coupling.
except, yes, apart from a coupling, that is right.
So,
So, the
tau dependence hasn't changed.
tau dependence hasn't changed, that's
Apart
right.
from the normalization.
That's right. That's right.
And therefore continues to be power law.
That is right, yes.
With the same power.
With the same power, yeah.
So 2 by Q.
Yeah.
So the powers are affected by me.
If you go to the deep IR, yes, that's correct.
So that sounds a bit odd from Sandeep's point of view. Right? You were expecting a new effective theory of excitations around the Fermi field.
But sorry, why is it? I couldn't connect what you said earlier.
You're saying that should be universal.
So I had thought that your point was that you turn on a Fermi field and your IR theory will now be about the excitations of the Fermi field, which should be a very different IR theory.
Okay. So why, but here the exponents are not changing.
Not changing, nothing really, not much is happening.
Oh, different.
Yeah.
I see.
Yes, that is true. That is true.
Deep IR, mu dropped out. No.
Yes, that would be the deep IR, yes.
I think mu dropped out, we get the same answer.
You get the same answer.
Good point. But then why is renormalization happening? Oh, it's some.
No, this is what, so okay, so there are two ways to do this, right? I mean, I can start with this and I can drop both of these terms and then I get the deep IR result. But what I can do is I can keep this entire expression, but I do a 1 over q expansion. So in the 1 over q expansion, I get exactly, when I say that you get exactly the Mulder-Stanford answer, what I mean is that not necessarily the answer that you get in the conformal limit. But even without the chemical potential, suppose I did not have this term, I could solve these two equations going in the large q limit.
I understand. But suppose we were interested in a slightly different topic. You
Yeah.
fix Q and go to the deep IR. Rohan made a very good point.
Yes,
Saying the equation looks like it's the same equation as without mu.
yes,
Because you're dropping the mu term.
That's
Therefore,
right.
you're going to have the same thing.
If you don't drop it, you get nothing.
Because
Yes,
mu term
exactly.
comes with the kinetic term, and you're dropping the kinetic.
But then I think, what it suggests is,
Mu term is not coming down. I omega is there.
Well,
yeah.
I omega is kinetic, but then you add I omega plus mu, and you're dropping the whole thing.
but I think.
No, that would be the strict IR.
Yes.
That would be the strict IR, but I don't want to go to the strict IR limit.
That's what I thought, because your
Yeah.
mind was.
Yes,
so
yes.
I thought because what you were doing was you're saying, I'm going to go to omega going to 0, I'll drop the I omega, I won't drop the mu, and I'm going to then solve.
Oh,
those-
actually, I have not dropped anything. Okay, so let me.
Till now, but now when you try to solve it,
Yes, so in this, for example, I have not dropped I omega as well.
okay, I understand, but now let us try to take the omega going to 0 limit.
Mhm.
So at least in G, I start dropping the omega term.
Mhm.
But I can keep mu.
You can
and
keep the mu
sigma.
term, yes.
I thought then you got the solution you are presenting here. Because
That is right.
mu was here and this. That's what got me confused, because the natural thought might be that at low enough temperatures, that sigma will cancel mu,
Mhm.
and then you'll be left with x. That's the standard Fermi surface story. But okay, so at least he didn't drop mu. He didn't drop mu.
Yeah. I don't want to drop mu, then I would have absolutely
If
nothing.
you don't mind, just
Yeah.
at finite Q,
Yes.
if you could write out the equation and tell us what term contributes to the IR effect. Deep IR.
So, okay. And then you have sigma to be something, g square, etc.
So the deep IR omega presumably drops out. Does mu
Yes.
drop out also?
Yes. So I can do two things. One is I say I am in the deep IR in which sigma is bigger than omega as well as bigger than mu. So I can drop everything and I get the conformal result.
Then of course
Okay.
nothing will depend.
Then nothing will depend on omega or mu.
And does this happen in
No. So in the solution I'm interested in, what I'm saying is I'm not dropping any of this. What I'm merely doing is I'm saying that G is G free 1 plus 1 over Q.
No, I
Something.
understand. But suppose I go to the deep IR of the solution you're interested in, then does this happen?
Yes,
Then omega and mu are both dropped.
that is right.
It both be dropped.
Yes, that is
Okay,
right.
then I'm sorry, I misunderstood. Because your mu shows up in the
No, but here taking the deep IR limit somehow have to be setting this to be 0.
suppose your temperature goes to 0 and mu goes to 0,
Yes.
but mu over T is fixed.
Mm-hmm.
And omega somehow scales so that that mu term cannot be dropped. Isn't there, let me ask you this,
Yeah.
I have not, I think, understood exactly the deep infrared.
Keep the charge. I think keep the charge of your system. At least.
Yeah.
That would be the burden.
Keep the charge. Normally I would keep mu fixed.
Huh.
Then energy would go like mu plus
Yeah,
delta
yeah.
energy.
Except I think you keep mu by it.
Mu by T.
Which is this? Yeah.
I think it would be same as keep the charge.
Okay, normal metals, of course, mu is fixed and
That's
equal
right.
low temperature. Mu is fixed.
Oh,
What is
yes,
the mu?
that is right.
But okay, let me just come back.
Yeah, yeah.
Isn't there some kind of a deep infrared limit where you can throw the omega term away?
Mhm.
initially,
Mm-hmm.
But mu
Will
and
remain.
sigma are both compared.
Yes.
That's the kind of limit which I thought would be interesting and certain, right? Do you not see such a limit or?
So from the solution, I have to think a little bit. So you are trying to say, so in the limit where, for example, I take this and I make it, so the right hand side is just mu minus sigma. What is the solution there? Can I read that solution from this one? That I have to look at it a little more carefully, but I think it should be there. See, I mean, this solution is written in the real space, so that's another problem. I don't immediately see where the omegas are. I have to take this solution Fourier transform, but these parameters are sitting, right? I mean, this mu. Okay, you can go to long distances. Then
Tau is time. Right?
tau is time. That's right. So then this is going to be the you can ignore this half, and this is the factor that will remain, where this nu is defined by this, where the effective coupling is essentially that object. So that's I guess that's one way you can sort of keep the mu effect.
Can I ask a question, please?
Yeah.
This Green's function at finite chemical potential, goes as I omega plus mu. So there is actually the frequency is complex.
Yes.
So I don't understand actually what you're saying, because you have a complex plane now, frequency complex plane.
Mm-hmm.
And in a sense, what is important here is omega square plus mu square.
That is
What
right.
does it mean to talk about infrared here? Tell me.
I think what I meant is really the modulus, not the complex number itself, but the magnitude, or for example omega square, if you like. I mean the way usually, if I do not have the chemical potential, usually people have this the Schwinger-Dyson equation in.
I understand.
Yeah.
I understand very well that. But,
Yeah.
I just wanted to understand the meaning of deep infrared when there is a
Mhm.
chemical potential. There is a scale already there. So are you
That's
saying
right.
that J square is much bigger than omega square plus mu square? Is that the point?
I think so. Yes. I think so. Yes.
Does that take care of this question Sadiq was raising?
That I'm not sure.
I mean, there's a physical question. You fill up the vacuum with a certain number of
Yeah.
electrons. What is
Yeah.
the effective low energy here?
Yeah,
Yes.
mean, that physical question has to have an answer.
Yeah.
Right. I was somehow thinking that maybe it's a different kind of limit. You know, at least normally when we get Fermi liquid behavior with a specific heat going like whatever it is,
Yeah.
linear NT or something, what happens is mu roughly cancels the energy of the Fermi surface, and then you're left with a small residual energy. Right? That's the system we talk about. Is that what you're doing? That wasn't clear to me whether that in the end was what you were doing, or whether you somehow just had very small mu. I don't know.
I think I'm not isolating that part, that question that you are asking, but that I believe should be, I mean, in principle that can be done.
See,
Although I'm not sure that's.
very interesting if you got non-Fermi liquid like behavior here, right? Or something like that. I mean, which maybe the system does. After all, it's showing chaos on saturation, so it's far from weakly coupled.
So you were saying to take a limit in which I can ignore I omega or omega for omega square if you want, but still keep mu in the sense that mu and sigma are of the same order, and see what happens in that limit.
And then tune that difference.
You know, the two Green's functions should behave differently. Because one is sort of like the Green's function for particles,
Yeah.
and the other one is for antiparticles.
Yeah, good
Right.
point.
And you're taking a mu, which fills it up with particles, not with antiparticles.
That's right.
So you should, in what you are doing, everything seems modelized.
Time reversal and there should be some, I don't know whether it's time. Charge conjugation.
Charge conjugation. Charge conjugation. Yes.
In the answer that you gave, it looked
Yeah.
very much like it wasn't making much difference, right? Sine of mu wasn't the
Sign of.
G of tau and G of minus tau will be
Yeah.
more or less similar, or no?
Well, I mean, they differ in this way, in this sign essentially, right? Because this G is what enters here.
I see.
That's the argument of the function, and they differ in here.
I see. And can you see that that is a dramatic difference in some limit?
Well, I mean, if for example, if you are in the limit where tau is order beta, then they can be quite dramatic. Well, I'm not sure quite dramatic because this is going to be still, I mean, what I'm saying is that this is a half, so I can either enhance it or cancel it.
You know, Fermi surface behavior is beta going to infinity,
Yeah.
holding the charge. You
Mhm.
be at zero temperature with a fixed number of electrons around there.
Mm-hmm.
So somehow if you tune that limit,
Yeah.
you should see a big difference, I think, between the propagator, the G of tau and G of minus. Because one of them should be essentially very massive. And the other one should be W, the low temperature, low energy charge.
I understand what you're asking, but yeah, no, this is not something that I think I have looked at carefully. But what I can see off the top of my head is, I mean, this sign can make a difference if I tune tau in the right way.
It will be interesting to look at this.
Okay.
I mean, just to physically keep the charge fixed.
Yeah. Right. Good point. Yeah. This is not something that I looked into carefully. Okay. Okay. So I forgot where I was. Yeah. Okay. So actually here, what I will from here go on or to calculate is modulo these things. I mean, in the 2-point function, we are not really going to do much. Although I now see we should, but okay. Instead, I will very briefly talk about this 4-point out of time ordered correlation function. So essentially, one needs to calculate a function like this, where sorry, I should not have put this t here. There is actually no time ordering, and at large n, what happens is this quantity is essentially a sum of ladder diagrams of this sort. So this curly f's are. So this thermodynamics is, I think, worked out to certainly a large extent by Sachdev and friends. I don't quite remember what they got, but yeah, there is. I think more or less, yes. For sure, yeah. So that part is somewhere there. So Maybe it's part of the reason why we kind of did not look into it, but if I remember right, they also have a chemical potential. They for sure have complex fermions. Okay. So, all right. So you have to sum up certain ladder diagrams, and the way to sum this up is actually known. Is essentially you can rewrite, if you like, the n+1th order ladder diagrams as an integration over a kernel. And in terms of pictures, and basically what it means is if you can calculate this kernel, then you can calculate the answer. That's the essence of the story. And roughly speaking, these are the diagrams that you need to sum. And as you can see, that if I have to calculate this particular diagram at this with these two loops, if you like, I can equivalently re-express this two-loop diagram as a composition of a kernel with a diagram at one order less.
Just one more comment about this.
Yeah.
You know, in the large n limit in 2+1 dimension, in large nth limit, it was believed for some time that the large nth limit gives you a controlled calculational theory of about the Fermi cycle. And then this guy from SYK-type showed that was not the case. What happened when you went low enough in energies, even at large n, non-planar diagrams started doubling. This is a consequence of some IR diagram.
I see.
Okay. So it's just a caution. It could be that something similar, though I don't see how, but it could be something similar.
Okay. So you're saying that non-planar diagrams start having some divergence, which become of the same order.
Yes.
I see.
And has to do with Fermi cycle.
I see.
So it turned out that even in the vector theory, somehow understanding the dynamics of this non-Fermi liquid was about as difficult as solving large n matrix.
Ah, okay.
If you take n to infinity first, what you going to get the exponent of order and what will become the
Well, if you take n to infinity first, it doesn't matter. But then your behavior is very boring. Everything interesting happens when you go to omega of order 1. Something like that. Yeah.
Okay. Good. Okay. So this is just simple diagrammatics. I can see that this battery is dying out, so maybe I should try to conclude quickly. Okay. Yeah. Well, anyways. Okay. So basically, at the end of the day, this is more or less standard in the literature to how to calculate this kernel, and what it does is, or what it is given by, is essentially some known expression in terms of retarded Green's function and the Whitman function, and therefore it's a calculable object if you know the Green's functions, which in this case we do. Of course, in the conformal limit, usually people use conformal symmetry to write that down, but in the large Q, you can also write it down. And the standard practice here is, this is what essentially SYK-type suggested, that if you really want to calculate this out of time ordered function, what you calculate is an object like this, where you separate each of these operators at 1/4 away in the thermal circle, and you take the limit in which this real times T1 and T2 go to infinity. And what happens to the whole treatment is that this function now is basically an eigenfunction of the kernel operator with an eigenvalue 1. So this is what you have to find, and if you use an ansatz of this form, that your f actually goes like this, then you can indeed find that this is indeed the eigenfunction, provided, and with eigenvalue 1, provided you identify lambda with this parameter. So that's essentially the outcome of the calculation, which is very simple at the end of the day. So this nu is essentially the parameter that appeared in here in terms of the effective coupling. But now that you have this, you can of course ask how does exactly this behave as I tune nu? In other words, as I tune the beta mu and beta j to begin with. And those one has to unfortunately get or plot numerically, but that's not too hard. So for example, this is one particular picture which shows how it behaves. So this is the vertical axis is lambda in units of 2 pi t, I think. So the maximum it can get to is 1. And if I lambda is the Lyapunov exponent. Lambda is lambda L essentially. So this is the object that you can extract out of this calculation, and then you can see that as the coupling becomes stronger and stronger for beta mu equal to 0, so which is the usual almost SYK with complex fermions, what happens is this rate curve actually goes all the way to saturate the bound. However, what you can see is if I have relatively small number, which is 0.9, even at this order of beta j, I see a significant change in the Lyapunov exponent.
I'm really confused. I mean,
Yes.
You mean you don't have the breaking of time reversal invariance in general?
Time reversal invariance is broken here.
Has to be, right?
Yes,
Because the way
yes,
you-
yes.
I thought just in the Schwarzian action would make you satisfied with chaos power. You know, just the 4-point function from the
Yeah.
Schwarzian term satisfies the chaos bound, and that dominates at lower energy.
Well, but now the low energy effective action has in addition a new light mode coming from this charge excess. It will be essentially a sigma model for the charge. And then the two will be possible.
This is what maybe you yeah.
What's the other light mode? I don't understand. There's no flavor breaking also.
No.
Okay, so what's the other one?
It's the mode for the U1. Let's set the chemical potential to 0. So now there is another, you see, the Schwarzian action can be thought of as you know, but suppose we go to the deep IR and the kinetic term is different. So now we could have phase rotations of the fermion independently at different times. This is a symmetry of IR, which is kinetic term. So we've got a phase function as a function of time. There is another zero mode. Psi goes to e to the power I alpha psi. That alpha is also a zero mode in addition to these zero modes.
That doesn't contribute to the bond.
I don't know whether the Schwarzian maybe calculates the bound, but it contributes to the low energy effect. Exactly. It will be basically a del alpha. And if you do the calculation, you get the same dependence of the coupling, 1 by j.
Can I ask a question? Hello.
Yeah.
Please, explain.
Yeah. So clearly there are two low energy, two functions describing the low energy theory. As Chirag said, there is the phase and then there is the reparameterization function. Now, what I understand actually from various people's calculation is that the contribution to the large time behavior from the Schwarzian is the usual exponential with the saturated bound, 2 pi upon beta. And then there is a growth term actually which is linear. This various people including Jungi and Chirag and company and some other people have also done. Now, there is no modification of the exponent there. So this is why I'm a little worried whether you have a coupling between the two types of zero modes also present to bring this about.
I see. Okay.
To raise this question.
I see. Actually, let me just to understand what Spanta is saying. So the other soft mode is not giving rise to an exponential growth.
Yeah.
That's yeah.
It's not giving rise to an exponential mode, which at least if it's uncoupled to the Schwarzian, you will see that it is basically sigma mode. And all your exponential, your growth is coming from the free solution of this action. So the fact that the Schwarzian has a free solution that grows exponentially is the heart of this exponential growth. On the other hand, sigma models only have powers.
But this is
Now, actually, we only looked at these non-abelian kind of things. But in Sachdean's paper, there was some coupling between the U1 and the
I mean, the sigma model has to couple to time reparameterization. No? If it's something like dt phi square integral dt won't be invariant
Yes.
under time reparameterization.
Huh.
Yes.
So there's bound to be a coupling.
Huh.
This is called pseudo-automatic.
Okay.
You write the
There
stress
is a
tensor.
coupling. See, there is a coupling because once the moment you make a reparameterization transformation, then you have to make a gauge transformation on the gauge field to restore it back to mu. So there is a coupling actually, and that is written in the Tasvir paper.
Yeah, yeah, yeah.
I see.
This exactly. This, yeah. The kind of coupling you're talking about sounds at higher than quadratic.
Yes.
Whereas you're just looking at the quadratic effective actually. But maybe when, as Penta saying, maybe when there's a non-zero mu, that, you see, if you've got some higher than quadratic coupling, but then you saturate some of those with a mu, it changes things as quadratic. That's what I don't know.
Yeah, I don't know either. I mean, this is,
I mean, but this has got to have a low energy
Yeah.
explanation, right? I mean,
yeah, yeah.
it's quite striking. Charge black holes during the chaos bound losing nuclear charge universally. Do you expect that to hold? Look at the charge sector.
In the deep IR, there is some confusion. I think the answer is yes, because the reparameterization there works along with the gauge transformation. So, if you consider the gauge transformation, then you can, I think, recover the reparameterization. Although this is, yeah, I have to say I have not really looked at it very carefully.
So there is a question.
Sir, usually in Mandelson's calculation, there was a 1 by j corrections to Lyapunov exponent, right?
1 by j, okay.
1 by beta j corrections proposed by the beta, and then there was systematic 1 by beta j corrections coming from the non-zero modes, which I think they calculated to first order or something.
Mm-hmm.
But I was thinking like you have an effective beta j which is different, right? So
That's right.
it could just be coming from the non-zero modes. This decrease of this decrease from 2 pi by beta.
Oh, I see.
I see. You're saying it's only to leading order in 1 over j that the Shortian action is the dominant thing, then of course there are corrections. Is that what you were
Yeah.
saying?
Yeah. I mean, it's totally understandable because there's the, even in the gravity side there's a 1 by alpha prime correction, and only in the real geometry limit you will see the Kundu by the beta,
Yeah.
and if you go to a smaller coupling you will not see this by the beta. And this somehow, this beta j is just like totally minus calculation except for a smaller j. It's effectively one.
But suppose we took the Mandelson's calculation took tau to infinity. So one of the effective coupling. Well, I see. You're saying that beta j. Yes, in suppose the beta j is. Yeah, it's probably true that you need to take beta j to infinity and tau to infinity to get the upper answer. Actually, I don't know. Is that right?
Could be.
Right, I mean, beta j
I think
infinity
Could be, yes. Yeah. I think that is what he's saying.
Strictly speaking, that is right.
Yeah.
Otherwise, you'll get correction.
Yeah, you get correction.
I think what he's saying is also tied to the what is the IR here, because if I ignore mu, then I don't have any j tilde here. Then you get the exact Lyapunov exponent saturation
See,
and nothing
I
else.
was going to ask you that for the 4-point function, it's not the case that you map to Mandelson's Stanford with j replaced by j tilde.
You do.
But in Mandelson's, as long as j is large enough,
Yeah.
up to corrections that he's talking about, lambda is just whatever it is, right? 2 pi over.
That's right.
Now, how come you don't get lambda?
No. Yeah. But I am here not plotting with respect to j tilde. This is j.
No, but what does it matter if for all values of j in Mandelson's is about one value of lambda?
No. But
I think these calculations map j tilde of Arnab will look like j of Mandelsena. So
Yeah.
it will be like some leading orders in 1 by.
It looks like that.
yeah, I think so.
Only in that limit,
Yes.
large j tilde.
Yeah.
This
Here it is not.
Large j tilde,
So-
that's the difference.
And that is what this. Yeah. I think he's right. That is what.
All right, okay.
that is what this suppression is about, and because of this exponential sitting here, even a very small mu will actually bring it down.
I see, okay.
I think even the 2-point function won't look like power law, right? If you
Yes.
start going away from this red curve, like the dotted curves.
Yes.
If you probably plot 2-point functions, it will not be power law, right? Because it will be like having the 1 by j corrections to the
1 by j
power,
corrections,
like
that is right. Yes.
Yeah.
Yes. Yes.
So in the strict conformal limit, you cannot go down in this red color. This is what I found out. Yeah.
That's right. I think he's right.
Well, I think we need to do a little calculation, involving the two effective actions which appear in Sachdev's paper, in which the phase mode and the reparameterization mode are coupled. I think it's a simple calculation to see. I mean, I have not done it, but whether the coupling of these two variables changes anything about the classical solutions of the Schwarzschild, whether it's just a simple shift of some sort, or I don't know, I have not done it, but I think that's the question to answer really, from the viewpoint of effective action.
I mean, here even the Schwarzschild is mixed, because to see reparameterization you get this and eclipse.
Yes.
So this is a Schwarzschild, not in the, just in terms of.
Yeah. Yeah. I think that is right.
And that calculation was not done by Sachdeva. I mean, they set up the
I will-
he may not have done it.
I don't know.
Okay, but you're right, Smita. Okay.
Yeah. No, I'm not sure if they did the zero mode analysis. Yeah,
For
but
the picking, come on, guys. Candy.
yes, but yes. Yeah, I mean, we only started kind of thinking about it after seeing Shiraj's paper, but it's actually quite dense. So we are still kind of trying to. Okay. After seeing this, I don't think there is. I mean, there is another plot that I can show you, but it's essentially the same story. It's just that in terms of this beta mu, which I have at the, if you like, at the SYK level, SYK Hamiltonian level, I can actually bring down the Lyapunov exponent, etc. In this sense, and this sensitivity is exponentially high because of the way that the effective coupling is defined. Okay. So, a very brief summary of what I try to discuss today is actually something very simple at the end of the day, I think. Although, yes, I understand the confusions and the questions that needs addressing. That this exponent is a very sensitive function of the chemical potential, at least seen in this way. You may be able to reinterpret it in other ways. And the large Q analysis is just for convenience, at least I think that this is going to be true even at order order 4 values of Q or so, but it will be much more difficult to compute. And a similar analysis or a similar picture will also prevail in if you try to do this flavored SYK, and I believe other similar generalizations along the lines, because at this level everything is kind of mapping the Hamiltonian parameters to an effective dimensionless parameter. So that's I think the story will be. Okay, so finally, of course, the outlook which you are, well, I mean, yeah, okay. So there's an elephant in the room in some sense, which is people are trying to figure out in terms of, for example, how to realize such models in terms of brain constructions, etc. There's actually something which kind of kind of intrigued me a lot into this whole game, although I made maybe I made negative progress in understanding that, but it was this 4 Fermi interaction. I mean, there is one way you can sort of generate 4 Fermi interaction from brain constructions, but by considering intersections and whatnot, but it seems a little tricky. Yeah, so if you, for example, take one of these models where you have a background, as in, for example, say I have a D3 brain and I stick in bunch of D5s, in a way that the intersection is just one dimensional. Only the time direction is shared, but then there will be indices on the adjoint gauge field, for example. Now you can try to integrate those out and see whether these couple fermions become 4 Fermi interaction. But it's not quite
So
as
to get more
simple.
content, won't it be much more like a matrix model rather than this particular index structure that allows you to sum Mellon diagrams? Is there a way by brain constructions to get this index structure?
You mean the matrix? I think it might be more, it might be simpler in the complex fermion picture, because there you have arrows on the propagators. So there I can try to make it look like matrix models. Even though,
No, I was trying to put it the other way around. That is,
okay.
usually, what we get out of brain constructions are more matrix theories, right?
Yes.
And then if you try to break the matrix, you still get bifundamentals, which are
I see. Yeah, yeah, yeah.
larger and
That is
solve.
right. That is right.
Here, there's a very different kind of index structure which allows you to sum one class of diagrams.
That is correct.
And makes it tractable to a field. Is that kind of index structure, can it come out of brain constructions?
No, not obviously. No, that is, yes, that is true. I mean, yeah, yeah. Yes, that is absolutely true. So yes, I mean, this is complete. I think, I mean, I have, at least I have no understanding of what to do, no concrete understanding for sure. Now, you can take the viewpoint which Gross Rosenhaus have been doing in a series of papers. They're as far as I understood, the goal is to, in some sense, calculate the bulk, in the sense that you can keep computing higher and higher point functions of such models, in the hope that you learn something at the end of the day about the bulk. So they are quite, I mean, they are looking at the original SYK, and by that I mean the Majorana fermions, but of course you can try to do that with complex fermions, and in some sense the resemblance might be more familiar, in the sense that, as I said, that you can put arrows and then things can look like matrices, etc. So you can try to calculate higher point functions in the conformal limit, etc. And of course, this question of seeing how the Lyapunov exponent change or respond to conserved charges, this part is something I am not quite sure about, but it looks like you might be able to do some calculations along the lines of Schenker and Stanford that they have been with black holes.
But there it's always
Yes,
very
this is the part that confuses me, so I don't know how to see that.
non-extremal situation I know of is always just
Always the
just because that's very universally the relative solution or whatever.
I see.
As far as I can see.
I see. But there might be, I
In a
mean,
limit where
yeah,
gravity is a good approach.
gravity is a good. So maybe higher derivative theories might give you that. I think that's what Prithvi was also
Yeah,
saying.
Sure. No, I just meant for that.
Yeah, yeah.
Yeah,
So
sure.
that might actually show up, and that may also be doable. I don't know.
Would expect,
That-
right?
that you would
Since,
expect, yes.
weakly coupled field theories is don't
Yeah, yeah.
this accuracy.
Yes, yeah. Okay, so yes, I think that's about it. So thank you. Thanks a lot.
Questions, ICT?
No question.
No.
Thanks for your comment.
Yeah, that was very helpful.
Questions we have?
Maybe I can ask one question. So,
Yeah.
do you think this thing can be computed from the bulk side also? I mean, let's say you put, I don't know whether this has been done, but charged geodesic computation. Charge geometry in the geodesics in charge geometry.
As far as I have understood, I mean, this actually goes back to what you were saying. I mean, I think classical I mean, Einstein gravity may not give you any, or probably will not give you any correction. What corrections you might receive is likely from the higher derivative terms, for example. So there you can do a. I have not computed, but as far as I can see, I think always you get, basically this is what Sandeep was saying, that you always get this 2 pi over beta answer. It does not
that
matter.
Is for radius Vaidya kind of null shell falling, right? Shell trajectory, shock waves.
That's correct. Oh, you want to add.
But now you want to charge because if you are uncharged, if you put uncharged shock waves, of course it will not care about charge, right? You will have
Yeah.
to put in some charged shocks. to see.
Well, I mean,
I don't know whether this has been done, but yeah.
I don't think it has been done, namely analyzing charged geodesics scattering in, for example, around a black hole horizon. I don't think this has been done. I'm not sure. But I don't think you would expect a change there as well, precisely because of what you were saying, because the lambda receives corrections from 1 over inverse coupling. That would be presumably related to higher derivatives, yes.
Probably if you rig the setting such that so like here we saw that
Yeah.
to see in the IR you needed both diffeomorphism and gauge function.
Yes.
So if you set up a bulk thing where when you see this that the IR to get the reparameterization of the IR you basically have to do a diff and also a gauge transformation of the charge. Because that is where your thing is becoming.
Maybe I'm not sure, but yeah. I'm not quite sure that will give you a different.